Hi friends, welcome back. Here we are going through ideal gas mixtures. From this topic you can expect 4 to 6 marks. So this is an important topic. Let me ask you some questions before we are going further. Why air coolers are effective in North India and why it is not effective in Chennai and Mumbai? How rainfall is happening? How fog is forms? On a summer hot day, when you feel more set than usual day, some people predict a possible rainfall, and sometimes they are lucky too. What made them to predict this? Answer to all of these questions and many more exciting things like harvesting water from air can be learned and enjoyed from this topic. Let's go through the syllabus of this topic, that is ideal gas mixtures, Dalton's and Amagat's laws, properties of ideal gas mixtures, air water vapor mixture, and simple thermodynamic process involving them, specific and relative humidities, dew point and wet bulb temperature, adiabatic saturation temperature, and finally psychrometric chart. That involves all of the syllabus of ideal gas mixtures. Dalton's and Amagat's laws are not new to you. You might have heard this, at least you might have heard this name before, right? They are simple and straightforward. You can learn them fast. All of these subtopic I am dividing into two: study of gas mixtures and study of moist air. By saying study of gas mixtures, what I mean to say is that a mixture of various gases like CO2, H2O, O2, N2 and all. When we consider moisture mixture, it is nothing but we'll consider all of air as a mixture of moisture and air. We will not subdivide the air into CO2, H2 and all. We just consider air and moisture. That is the difference between how we consider gas mixtures and moisture mixture. Let me give you a question from gas mixtures. At this point, you are not expected to answer this question, so just sit back and listen to the question just for fun. Okay, this is a question from GATE. Volumetric analysis of hydrocarbon combustion product shows 8% of CO2, 15% of H2O in vapor condition, 5.5% of O2 and 71.5% of N2. The combustion product flows steadily through a heat exchanger at 200 kilopascal pressure. Assume each component in the mixture to be an ideal gas. In order to avoid the condensation of H2O in the heat exchanger, the minimum allowable temperature in degrees Celsius is. And later they have given saturated H2O table also, that their pressure and corresponding temperature in degrees Celsius is given. That means at 10 kilopascal pressure it will be 45.83 will be the degree Celsius. That sort of question is to be coming from the first part, that is study of gas mixtures. Then we go to the main part, that is study of moisture. This is the most interesting and wonderful topic. Here you will learn about what is specific humidity, that is omega, that is defined as the ratio of mass of vapor to the mass of dry air in a certain moist air. That is omega equal to mv by mv. mv means mass of vapor and mv equal to mass of air in that mixture. I told you that when we consider moist air, it is nothing but mixture of vapor and dry air. That's how we consider. We will not consider the percentage of nitrogen, oxygen and all separately. Okay, I hope you understood that point, right? So omega is generally expressed in kilogram vapor per kilogram of dry air, and obviously the kilogram of vapor that is going to be in moisture will be very, very less quantity, so the omega will be very a small quantity. And water vapor in air exists as a low pressure, and therefore we can treat water vapor as an ideal gas. Remember, when we will consider a gas as ideal gas, we have seen the conditions earlier, right? When the pressure is very low or temperature is very high, we can treat them as ideal gas. Here water vapor in moist air exists at very, very low pressure, very low partial pressure, maybe 1 or 2 kilopascal, and we know that the total pressure, that is the total pressure of air, is 100 kilopascal in normal conditions. So there 1 or 2 kilopascal is very less. So we can treat water vapor as ideal gas. So we can put ideal gas equations and we can find some beautiful relations for omega, and finally we'll be getting Omega is equal to 0.622 into PV by PT minus PV. Here PV means partial pressure of vapor and PT means the total pressure. Generally it is used to be 100 kilopascal and PV will be ranging from 1 to that range, it will be like that. And then we will be having relative humidity denoted by phi, and it is defined as the ratio of mass of vapor to the mass of vapor under saturation condition. It simply shows how much is the moisture carrying capacity of that air. If the relative humidity is 100%, we can say that that particular air can not longer carry any more vapor. If the relative humidity is 60%, we say that it is having a lot of capacity for carrying vapor. So that's what happens in North India. Their relative humidity is very less, so whenever the moment we sweat, it can absorb that sweat, so we won't be feeling that much itchiness. But in the case of South India, like cities like Chennai and Mumbai, the humidity, since it is close to seashore, the humidity of air is high, so there or nearly 100%, near to 100% or 95%, something like that. The moisture carrying capacity of that air is very less, so people will sweat. That the same way why coolers are not effective in Chennai and why it is effective in North India. I'm not going to explain how it is. You can think about it. If you are not still getting, you can Google it and find it. And phi will be getting PV by PVS or MV by MVS. PV is nothing but partial pressure of vapor. PVS means partial pressure of vapor at saturation conditions. When we go through this topic, you should be knowing how to represent the condition of vapor in a TS diagram. That is very, very important, and it is simple too. If you are gone through the properties of pure substance, this thing is very simple, a left hand job only. Okay, and there comes the next things like dry bulb temperature, wet bulb temperature, wet bulb depression, and I'm not going through the details. You will understand when you go through it. Then comes the dew point temperature. Dew point temperature is defined as the temperature at which water vapors in air starts condensing. This explains how you see dews on leaves in some morning, right? And later we will see one important other topic, that is mu or percentage humidity is given is equal to omega by omega s. Omega, we know that it is specific humidity, omega s is specific humidity at saturation conditions. So it is defined as the ratio of actual specific humidity to specific humidity under saturation conditions. And we can find the enthalpy of moist air with some relations, enthalpy of water vapor also. That completes our basic things on this topic, and here we are ready in a position to go through psychrometric chart. We know that from TS diagram, as PV increases, that is partial pressure of vapor increases, corresponding saturation temperature is also increases. We have seen this from properties of pure substance, that is when pressure increases, corresponding saturation temperature also increases. Same way here I am including just saying partial pressure. So we will plot this for different partial pressure temperature combination, and finally we will be getting some curve for that saturated vapor condition. So on left it is subcooled liquid, on right it is superheated liquid or superheated fluid. And similarly, when we learned omega, that is specific humidity, we have seen that it is nothing but MV by MA, or it is equal to 0.622 into PV by PT minus PV. So it is a function of PV because PT is a constant thing. So here what we are going to do is that earlier I said that we will be drawing a plot with temperature and pressure. Instead of pressure, I will just replace pressure with omega. So it's a plot of temperature and omega. That is nothing but psychrometric chart. And in psychrometric chart, we are mainly interested in superheated fluids, not on subcooled fluids. And so we are more interested on the right hand side of the plot. I'm sure by this time you will be wondered what this guy is talking about, right? I'm just giving an introduction. You are not supposed to know everything in detail when I am talking. I'm just giving a detail some intro, so that when you go through the topic, you'll be able to reconnect things and it will be more advantageous for you. So psychrometric chart is a plot between temperature and omega. There are some basic lines or curves in a psychrometric chart. I'll just go through it. That is, first, dry bulb temperature lines, constant specific humidity lines. You know that dry bulb temperature lines will be a vertical line and constant specific humidity lines will be a horizontal line, because our graph itself is omega versus T, right? And thereafter we have constant enthalpy lines or adiabatic lines. We will see how it is coming. Constant specific volume lines, constant relative humidity lines, constant dew point lines, constant wet bulb temperature lines. These are all really interesting, and various phenomena can be explained through this, and a lot of times some questions used to come from this topic. This is interesting and you can expect a simple question from this topic. And there are some basic psychrometric process like sensible heating, sensible cooling. Sensible heating is nothing but a process of heating the air at constant omega, and similarly sensible cooling is nothing but the process of cooling the air at constant omega. So the path will be a horizontal path, because omega will be constant, we are just reducing the temperature, so it will take a left hand side arrow. There are some implication involved in that, you will learn later. Thereafter it is pure humidification, pure dehumidification. These are all the pure process, but pure process are not possible many times, so there will be a combined process, that is heating and humidification, cooling and humidification, cooling and dehumidification, heating and dehumidification, like that. That completes our syllabus, and let's see some of how the questions are coming. Possible questions involves finding omega, phi or mu from basic given data. They are all straightforward questions, but still you will have to spend some amount of time so that it will not be a suspense thing when the same question comes to you from examination. It can be a bit tricky also, so you are advised to go through and find some time for finding the omega, phi and u questions. And there will be basic questions related to WBT, DPT and DBT as well, that is dew point temperature and dry bulb temperature and wet bulb temperature. Thereafter questions involving psychrometric chart. These are all some basic questions, but having familiarity with these questions will definitely help you to solve advanced questions. Good thing is that by spending 1 to 2 hours with above questions will clear all of your questions and will be ready for attempting any advanced questions. Ideally, you will have to spend 12 to 15 hours for concept learning and 5 hours for problem solving. It's a bit new and bit lengthy topic, so you should spend this much time if you are new to this topic. If you are already having familiarity, the time will be considerably reduced. Okay, that's all from this topic, and next we'll go through thermodynamic relations. It is a simple topic and you can expect 3 marks on an average from this topic. Here are some thermodynamic relations are there. These are all derived mathematically. Let me go through the syllabus. Syllabus involves TDS relations, Helmholtz and Gibbs functions, Gibbs relations, Maxwell relations, Joule-Thomson coefficient, coefficient of volume expansion, adiabatic and isothermal compressibilities, Clapeyron and Clapeyron-Clausius equations. Mainly Maxwell equation. There are 4 equations in Maxwell equations. You should know all of these 4 simple relations. Even though you are not expected to know the full derivation, you should know from which equation each of these 4 equations are came. That means there will be known 4 equations. There are already from these 4 known equations we are deriving these Maxwell relations. Then there is TDS relations. There are 2 TDS relations, and there is couple of relations between Cp and Cv. Even though these relations are derived mathematically, there are specific physical implications are there for these equations, so you should understand them. If you are aiming for any higher studies in thermal science, you should know these things very well, so this will help you a long way. Then there is coefficient of volume expansion, isothermal compressibility, adiabatic compressibility. Then comes one important term, that is Joule-Thomson coefficient. This is really important and very interesting also. Questions from this topic is very common also. Then comes Helmholtz and Gibbs function, this which you might have already familiar with during availability portion. Finally, we are having Clapeyron and Clapeyron-Clausius equation. This is also important. There used to be questions from this topic, like for example, the question from this topic is to be general question. Okay, it's like they'll be giving the boiling point at particular pressure. Like for water, the boiling point at 100 kilopascal is 100 degrees Celsius, right? That means at atmospheric condition, the boiling point of water is 100 degrees Celsius. So what will be its boiling point when the pressure is 80 kilopascal? These sort of questions can be solved from Clapeyron-Clausius equations. Ideally, 2 to 4 hours of preparation should be more than sufficient for thermodynamic relations. So that completes all of our syllabus in thermal science and thermodynamics. I hope you are going to have a very nice day with thermodynamics, and you are all going to score very good score in GATE, and you will be getting sufficient rank in such a way that you can fulfill your dream. All the best, students. Bye bye.